When a soil begins to desaturate, or let's be clearer, when the water boundary reaches the soil, menisci hang from the soil because the water likes to wet the soil and pull the soil out or down. In addition, they put the water in suction, so the water pressure decreases below what would be otherwise hydrostatic. So then we wonder, what are the forces that are going to be experienced by the skeleton and that will cause compaction and shear strength, etc. So the question is, what is the effective stress? And so under this particular condition here, the effective stress would be equal to a first order approximation, and we'll see how good this is. It would be the gas pressure minus the water pressure, where the gas pressure is everywhere here. So this is the pressure of the gas, and somewhere here we have the pressure of the water. And so this suction is the one that is pulling the soil down, causing it to consolidate. Now, we can add here a factor to make it proportional to that, to accommodate other effects, and we will see what is that factor. As a second step, now we could have the similar system, but we may add a slab to apply a boundary stress. And so here we are going to apply a boundary stress sigma. So this equation applies to the initial condition before I add a slab to apply the boundary stress sigma. When I do that, now the effective stress for the second case will be equal to the conditions created at the boundary, sigma minus u gas, because you see the gas is acting between them and pushing the slab up, plus the effect of the suction, lambda, and let's call that delta u. U gas minus U water. Please recognize that U water will be a negative value, so it gives me a positive value to cause this stiffening of the material. This equation is known as Bishop's equation, and it comes from the beginning of the 1960s, somewhere between 59, 60, 61. Let's see some implications of this equation. So let's start at the very beginning, when we are in a condition like the one we are describing right there, just before air decisively enters the soil. In this case, let's go back and analyze. We zoom in at the level of a particle, and it is what we had above. And so we can go back to the simplest equation, or to the more general equation. Please realize that whenever we put the meniscus here, they must have all the same curvature because they are sharing the same vapor pressure, and the suction is constant throughout the system according to Laplace. Therefore, if I analyze that particle in particular, and assuming that there is no contact angle, so this is the surface tension pulling down, plus in addition we have the suction, the force that I need to compensate, this normal force coming from the particle below, which is the skeletal force, which is going to give rise to the effective stress, that normal force is equal to, without the slab, without the external stresses, is going to be equal to 2 pi r, the perimeter, times the surface tension between the liquid and the gas, plus the suction acting on the lower part of the particle, also pulling the particle down. So it's going to be pi r squared if this is at the verge of air entry, so you are on the equator plane, pi r squared times delta u. Now, if we divide by diameter squared, so the equivalent area of influence of a particle, let's say in a quasi-simple cubic packing configuration, is going to be 2r times 2r. So if I divide by 4r squared, I get an idea. It's a way of upscaling from skeletal forces to the macro scale concept of effective stress. And so this is also divided by 4r squared, the same as here. And so what I get is that this is equal to 2 pi over 4r gamma liquid gas plus pi over 4 delta u. Now, to bring everything in the context of delta u in the form of Bishop's equation, so let's multiply here times delta u over delta u, and the difference in pressure, the capillary pressure between the air and the water, which is delta u, according to Laplace, imagine that you look at it from the top, and if you look at this simple cubic packing from the top, this pore that is going to create the depression for the capillary film, the interfacial film, and if you see this Pythagorean distance, this is 2r, 2r, and this is square root of 2, 2r. And then I have to subtract 1r and 1r, so it's going to be square root of 2 minus 1r. So this is twice the gamma liquid gas over r pore, where r pore is equal to the square root of 2 minus 1 r of the particles. So now we can replace here, and what I get is, therefore, I can cancel interfacial tension, I can cancel the pore size, these 2 with these 2, and I have pi over 4 and pi over 4, so this is equal to delta u factor of pi over 4, which I can also factor out, but let's keep it here, times square root of 2 minus 1 plus 1, so times square root of 2. And pi over 4, square root of 2 is 141, so 141 times 314 is a little bit over 4. In fact, this is 1.11 delta u. So I am making this analysis to get a first order estimate of how much lambda could be. We tend to think that lambda goes from 0 to 1. However, just before at the verge of air entry, lambda could be slightly greater than 1. So it's not just the degree of saturation. Next, we're going to explore the evolution of unsaturation and the possible implications on effective stress. Let's consider the following case. We have a soil that is totally saturated. The water table is above the soil, and then the water begins evaporating, so the water level begins falling until it reaches the soil. If I take a specimen here and I run an oedometer test, then I will start with a certain effective stress, and the system is totally saturated, and we know that there is an initial sigma z is equal to the sigma z initial effective, and that the sigma horizontal is going to be some value k naught of sigma z effective. Now the question is, what happens when the water reaches, this goes down, it reaches the water table and it continues evaporating, and if I zoom in here, now I have a situation where the water has reached the particles, is hanging from the particles, the water goes into suction, and we add the interfacial tension. Well, at this point, we have further compression from the top, and indeed, if we take something according to Bishop, we could say that the sigma z is equal to sigma z minus u gas, or u air, plus a lambda of delta u. And what about the horizontal stress? Well, this was exactly the same as having added more stress from the top. Everything is coming from the top and bottom boundary, So in this case, sigma horizontal effective is still K naught of that new value of sigma z effective. And so the sigma z has seen the full effect of suction. The sigma horizontal has not. The sigma horizontal has increased, but according to K naught of the increase in suction. You can replace this one here, and it will be K naught times lambda sigma u. Now, very soon, we are going to reach a situation where the soil, the water table is going to be way down here, and the soil is going to be under significant suction, and cracks may form. And between cracks, the soil may be perfectly saturated still. In the oedometer, what actually happens, if I look at the wall of the oedometer, the same thing occurs. Air enters the wall of the oedometer because it is less wetting than the mineral, and now I have the capillary meniscus here, and I have the capillary meniscus at the top. And now what is happening is the soil is being squeezed not only vertically, but also horizontally. So the vertical effective stress is still the air has not invaded, so lambda is pretty close to 1, or slightly bigger than 1, as we noted earlier. But now the sigma horizontal is not only the sigma horizontal due to the walls, but also due to the suction that has been created at the wall. The same would happen here. This is being pulled inwards and downwards. So there is an increase in the horizontal stress. Now, in the absence of a crack, or in this system, this stress increase a little bit relaxes the skeleton action against the wall, and so it's going to be somewhere between this initial stress and a stress that is going to be equal to sigma horizontal equal to sigma horizontal initial plus a lambda of delta u. So this is beginning to look like Bishop, but it's going to be somewhere in between, because now I have an interaction with the wall, so I have to go to the interplay with the skeletal stiffness to determine what is the new effective stress. So even in this case, Bishop may not have fully kicked in on the horizontal stress. There is one more situation as the soil dries. The soil is never perfectly homogeneous, and if there are heterogeneities and there are lenses with more fines than other places, let's see what would happen. So let's say that we have a whole granular material, the coarser granular material, surrounding a lens with finer grains. So imagine the evolution of the system. The water table has gone down, it began drying, now air has invaded all the large pores, but this lens with fines has small pores. So it is very likely that there may be a little amount of water remaining at menisci between the coarse grains, having some action pulling particles together. Remember, the curvatures ought to be the same. If you draw this carefully, make sure that you draw curvatures everywhere the same, because this is being balanced by the vapor pressure and the suction. And so we put the menisci at the boundaries here, and as you can imagine, this water between the large grains is under suction and is pulling the grains together to the extent of that small radius of the water at menisci called the pendular regime. However, all this lens is all surrounded like a latex membrane, which is the interfacial tension that is bringing all together. So all this is feeling the full effect of suction. So the effective stress within this lens is getting a squeeze, so the actual effective stress is higher than in the coarser skeleton. So one of the conclusions that we can begin deriving from this is that when there is spatial variability in grain size distribution, it will have implications on the field of effective stress, which will have a series of implications related to the evolution of strains and the evolution of strength in the soil mass. The previous example addressed the issue of spatial variability, heterogeneity. Now, what about the case of anisotropy? It is also tricky. Let's say that we have reached the pendular regime, whereby water remains only at menisci, and we create menisci, all of them of the same curvature, at contacts between particles. And the suction times the area affected by these menisci and the additional force of the periphery of the meniscus times the surface tension will determine the forces acting between these particles. Then if we do the area average of the forces, we will have an idea of what are the implications in terms of effective stress. As you can see, the size of menisci, the number of menisci per unit length varies when you have this geometry which we have exaggerated using lentils or rice grains. But this is actually the case of clays. And so we can conclude that the effect of suction is also going to be affected by fabric anisotropy. By the way, not delta U, the effect of. And to show once again the complexity of unsaturated soil behavior and the effect of suction on the behavior of soils, one would expect that as suction increases, there should be contraction. However, a collapsible soil starts relatively dry and with high suction. However, when you flood the soil, that means that you bring the suction very much down. You would expect the soil to swell, according to that basic rule that comes from the concept of effective stress. However, a collapsible soil actually experiences very high volumetric contraction, in fact, collapse. Therefore, we see the inherent limitations of a formulation like Bishop's effective stress. This was recognized, in fact, by Bishop and others early in the 1960s, and by that time, Fredlund and Morgenstern, among others, were beginning to say that probably we shouldn't combine the boundary stress with the effect of forces created internally by suction. And so we should be looking into whether it is a strength or a stiffness or volume change, instead of looking into a combined parameter, let's say Bishop effective stress, we should be looking at the boundary conditions and the internal conditions determined by the suction, and looking at the effect in a three-dimensional space. Why? Because that component and this component are not necessarily located at the same position, and they have different effects. So that they are independent variables. They are two dimensions, independent dimensions, in the three-dimensional space of a soil property, such as stiffness, strength, dilatancy, etc. And so you will find a large number of cases where the separation of the variables is the way to go. The multiple examples that I have presented here today, starting from a soil that is at the verge of becoming unsaturated until the water remains only in the pendular regime at contacts, begins to show the limitations of generalizing a formulation like the effect of suction on Terzaghi's effective stress initially proposed by Bishop. And in fact, there are multiple cases where the processes are contrary to Bishop's initial predictions. So indeed, we have to explore in every case whether the simplified and convenient formulation of merging suction with Terzaghi's effective stress is sufficient, or we actually need a little bit more complex but more versatile and physically correct approach in which we separate these two causal mechanisms, one that is happening at the boundary and one that is taking place locally, in order to properly anticipate the behavior of our soils and the performance of our engineering systems.